welcome to the in-practice tutorial for Electrical and Electronic Engineering 1A, 2011 Semester 1. Today I really want to be going through a primer on how to get started for the module, how to get the basics understanding, to get starting, to get building. First of all today, I really want to just cover the transformer that you'll find in your desktop. Looks like this, set up like so. Transformer to start with. Then I want to be going over, looking and discussing some things about the breadboard, how we go about wiring our breadboard. Here's a mock-up, and we'll go through that in a second. And roughly what this circuit's going to look like once it's completed. Okay, so with regards to the transformer, this is the device here, just a standard plug pack that you'll find from any Dick Smith's or JCar type store, Radio Shack, formerly used to be Tandy. What this device is a transformer that steps 240 volts AC down to either 12 volts AC or 9 volts AC depending on the unit. Functionally, as far as you're concerned, they'll do the same job, just we built them in a couple of batches. On the other end of this particular device, through the other end of the cable, you'll find a little jiffy box. On this it has some output screw terminals. This is what we'll be connecting our breadboard to at a later stage. On this device you'll notice a couple of LEDs. There's a red and a green one, and a couple of buttons. A black one and a red one. Just plug this in so I can give you a demonstration. Now when this device has got power to it, hopefully you can see in the video, there's a little red LED coming up. You can see there. And when I press the red button, green LED comes on to indicate we're getting power to the device, and power is going to come out of these two terminals. I hit the black button, it kills power, it kills everything to the outside. Okay. Operate, also, if you happen to short out terminals and create a dead short in anything that's connected to this, it'll also kill power as well. Operates much the same as sort of a safety switch you'd find in your power box outside your home next to your meter. Okay, cover these things. Alright. Next thing we'll quickly talk about is the breadboard. For the breadboards, I'll refer you to page 110 of the notes. There's a fact sheet upon how they work. But roughly speaking, you'll find that it has horizontal rows in it. In these particular set of breadboards that we use, these are connected, each horizontal row is connected together. You can see floating. Here's the one of the model that we're using in our practicals. There's a bit of a close-up for you. Everyone can see at home. Beautiful. Each horizontal row is connected together, and each vertical row of 5 that you can see grouped, each vertical row of 5 holes is grouped together as well. So if you plug a device into any one of those holes that's connected, it's grouped together, and you plug another leg into another, so you plug in something into a hole over here, another device into a hole over here, and because all those holes are connected in that big row, you'll have electrical continuity between the two. Same goes for these groupings of 5 here. Just to exemplify that, this is an old breadboard that we had that was broken. I've stripped the back off, stripped the insulation and so forth off. That's what it looks like behind. In this breadboard, you'll notice there's a break in here between the two halves, these horizontal rows. That's just because it was the style of that particular breadboard we were using back then. You see that's the front half. So those designs have changed over the years. Just be sure when you're working at home, working on a breadboard, you check the continuity of those. Alright. Next thing I really want to talk about is wire colouring. Okay. Wire colouring you'll see on an adjacent page, so page 111. Page 111 talks about why we want to colour wires and the differences between electrical wires and what it all means. The summary of which is black, when we're colouring wires in electrical engineering, black wires refer to ground, typically, and red will be reserved for positive DC or positive direct current. White, in this instance, for our project, we're going to use for unregulated DC for this particular module too, and we'll cover and discuss that, and you'll learn more about that later on in the practical in the session itself. And yellow we're going to reserve for AC, or alternating current. Why? Purely because the terminals that are on this device, I've shown earlier, that spits out AC. And to colour code and match. Wouldn't Carson Cresley be impressed? Alright, so next thing we want to do is, okay, so we've now talked about each individual component and how it all sort of, we want to colour code things and put them together. Actually, I'll just go quickly back. The reason why we want to colour code these things, colour code these wires, is so we can easily recognise problems that occur and we can debug them readily by looking at them. Typical instances where you might find colour coded wires would be Cat5 data cabling, single phase power to the home, and other complex wiring looms for cars would be another prime example. That's a reference to you, Matt, if you're watching. Instances where you might not want to colour code this is somewhere where you don't want the person who's going to be looking at the loom or the cabling to rapidly understand what's going on. That would be, for example, the Australian New Zealand standard for car alarms, which says all car alarms must be white black. Why? So the thief that comes along with his set of wire clippers can't come in and go, I'll just cut the blue wire because that clip will just disable the whole system and I can happily steal your car. If everything's all coloured black or all coloured the same, can't do that. Alright. So, back onto getting a connection from the power block, which is this device, down to your power board. Okay. What we want to do, guys, I've just done it just before we started the video, is I've cut myself a length of wire, or 2 lengths of wire in fact, about 250 millimeters long. Okay. Reasons for that will become apparent just shortly. On one end of this wire, guys, I want to trim off the insulation by about 5 millimeters in length. Alright, and I'm just doing that with my side cutters now. And the other end I want to do with about 25 millimeters of exposed copper. The way I'm doing this is straightening the line, and just pinching the insulation to create a weak point, and then I'm pulling it away. So I'm really not trying to cut through the insulation at all. Just trying to tear the insulation, create a weak point so the insulation tears, and then pull straight off the copper that's lying underneath. On the other end, as I said, we'll do one about 20 to 25 millimeters. There's one, and there's the other. Okay. Okay, so here's my 2 wires that we've just stripped and exposed. Alright, so what we're going to do is, if you open up the little power block in the end in the Jiffy box and you wind out the yellow terminals, you notice there's a couple of holes drilled through the posts. Feed the 20mm exposed length straight through them, then screw the terminal down. That'll trap the wire in and make sure that helps ensure that you've got really good electrical connectivity and you're not trying to clamp on insulation and you won't have a bad connection. If you try to wrap it around the post and screw the terminal down, what ends up happening, screw it down, what ends up happening is inevitably the exposed copper gets spat out the side and away you go. If you have more than about 25 millimeters of exposed copper, then what happens is the ends that you can just might be able to just see poking out here. If you had more exposed copper than that, then those ends might end up touching, and well, then you end up with short circuit and your circuit won't work anyway. That's all not good. So what I've chosen to do with my breadboard here, I've already put in my resistor. Okay. I've already located my resistor. I want to locate the resistor in around about row number 20, near enough, as you see it on the breadboard. Okay. Just stick that in there. There we go. Stick the other one in. I'm going to stick that in row 20. That's going to give us about some room to play with when we build subsequent modules. And these wires, as I said, we're grouping in vertical rows of 5. So one row can go on the bottom. One can go in that row. And the other can go on the top. Much like this. Okay. So for those playing at home, there's a side view in it, and where we go. Okay. So the reason I've wanted to make these wires so long, so I can move this around. Move this around when I'm on my desk and it's bumped, and not going to rip out. If you have really short wires that are about 6 centimeters long, as I've seen some students over the past couple of years do, you bump your power bowl, you bump your little Jiffy box, or you bump the board, and everything rips apart and everything ends in tears, and students sit there wondering why nothing works, and there's There's actually no power getting to the board. Okay, that's roughly what it looks like. So when you can power it up and away you go, all good and well. Everyone's a happy camper. So that's how to get that particular started. The reason why we want to place that particular resistor there is this is roughly sort of whereabouts, roughly row 20 would line up on this schematic or this picture that I've sketched of the breadboard. We want to build everything in our power circuit off to the left. Okay, so module 2 really wants to be self-contained here. And module 3, which is the clock section, we want to build that there, which will be starting in probably about week 4 of the semester. We're going to reserve this quadrant, this top left-hand corner, sorry, right-hand corner rather, for module 4, our 7-segment display decoder. And really, a lot of the rest of the stuff in module 4 we're going to run across the bottom. So the counter that we're building in module 4 will be located down here, an LED decoder, and finally the LED array that we're going to power up. It's going to look like a dice pattern, which is the end game that we're trying to chase down. Okay, there's a picture of this completed circuit. I believe it's on page 85. That's roughly, if you compare this sketch that I just made here with your workbook on page 85, see it roughly lines up. We can't, the reason, so if I start to spread my power supply well across the board, and I'm not going to have much more room to work much later on. Okay. As you see in your breadboard, we'll just sort of, so we're going to wrap up with a quick discussion on the resistors. As you see in your workbook on figure 14, the resistor that's spec there is a 47 ohm 5 watt resistor. Now you're going to have two types of resistors in your kit. One will be a 0.25 watt resistor. The other is a 5 watt resistor. Now, the rough power calculation is to the power that's going to be going to that. Remember, we're running on a 9 volt AC supply. So the power that's going to be consumed by that resistor is going to be V squared upon R. So it's 9 squared divided by 47, which comes out to around about 2 watts. So if you try to push 2 watts of power through a 1/4 watt rated resistor, it's not going to work too well. In fact, it's probably going to go up in smoke. Okay, it's probably going to go up in smoke, much like this one that I've rigged up here. So this is an example of, guys, what not to do. In fact, yeah. So let words speak themselves. I'm just going to grab a black backing board off screen. Just hopefully you can see what's going to happen. So I'll fire it up now. Alright, now hopefully with that black backing in place, you can see the smoke that's starting to rapidly rise off the component. Yeah, there we go, it's starting to glow. It's glowing some more. Come on, there we go. And there we have it, it's on fire. Alright, so I'm going to turn that off and wave some of the smoke away because that's really not good. Yeah, don't do that at home because you might burn the place and Mum and Dad might not be too happy. Maybe do it in the lab, but don't tell anyone I told you to do that because Stephen Guest, our lab manager, won't be too happy. There's an example as to why, guys, 1/4 watt resistors don't tend to like it when you run too much power through them. Alright, they tend to break. Magic smoke escapes. Electronics, guys, it's all about the magic smoke. Magic smoke needs to stay inside the component. If the magic smoke escapes, yeah, component no works so good no more. Okay. So, just as a final wrap up, refer to figure 19 as to how module 2 should be laid out on your breadboard.